Okay, so now let's take a look at 1667, and this one says, a listener doubles his distance from a source that emits sound uniformly in all directions. There are no reflections. By how many decibels does the sound intensity level change? So what we've got is, once again, we've got a sound source that's emitting sound power uniformly in all directions, and we're going to have another point over here which I'll call A. And this is a distance d away, and what we have at point A is some guy listening to the sound being produced by the source. So he's going to hear some sound intensity there. Then what he does is, tired of being at point A, he then picks himself up and moves himself to point B, which according to the question is twice as far from the source as point A was. So whatever that distance d was, the distance from S to B is going to have to be twice that, so 2 times d. And once again, for my benefit, the question says, by how many decibels does the sound intensity level change? So what I would like to do is think about, start with, perhaps not about how the sound how the sound level changes, but how the sound intensity changes. Because sound intensity is something that I can calculate from power, whereas sound level is this weird thing involving logs. But in any case, if we can figure out how the intensity changes, then figuring out how the sound level changes is fairly easy from that, because we can quite easily convert sound intensity into sound level. So let's first of all try to figure out what the intensity is at point A. Now, we're not given what the power being output by this source is, but let's suppose we did know it. And we could say then that let P be the power output by the source. And this is going out uniformly in all directions. So in that case, we know that the intensity at A, so we'd say then the intensity at point A is going to be IA is equal to the power being output by the source divided by 4 pi d squared, where again this just comes from the intensity is power divided by area definition, where in this case we're choosing the surface over which that power is passing through to be a sphere, with the source at its centre and the point A on its surface. And this 4 pi d squared is just the surface area of that sphere. And similarly then, the intensity at point B and at point B, we have a similar thing, but we're going to have IB is equal to the power divided by 4 pi 2d squared. Now, if we did know what the power was, then we could easily calculate these two intensities. And if we had those two intensities, then we could easily calculate the sound levels. And if we could calculate the sound levels, then we could get what the question is asking us for, which is the difference between the sound level here and the sound level there. So let's go ahead and from these numbers here, calculate the sound level at these 2 points. So here we're going to have that beta A, say, is going to be equal to 10 log IA divided by the threshold of hearing intensity, and similarly for point B. And then if we could get numbers for these, to calculate what the question is asking, we would just need to take this and subtract it from B to B, because that would be the amount by which the intensity level changes. So we would have B to B minus B to A is going to be 10 log IB on I0 minus 10 log IA on I0. Now this looks a bit messy. I think I would like to simplify this a little bit. So as usual, when I have this 10 log, a difference of 10 times log things, I'm going to factorize out the factor of 10. So this is going to be 10 times log IB divided by I0 minus log IA on I0. And now that I have this plain old difference of 2 logs, I can use that log law. So one of the log laws was that if you have the log of a fraction, then that is equal to the log of the number in the numerator minus the log of the number in the denominator. So we end up with that. And if we just apply this log law to this situation here, we could express this difference of 2 logs just as a single log. So then we're going to get that this is equal to 10 log what's in the first log, which is IB, divided by I0, divided by what's in the second log, which is IA, divided by I0. And here we have one fraction divided by another fraction. And when you have one fraction divided by another fraction, that is exactly the same thing as the fraction that's in the numerator multiplied by the fraction in the denominator, but just flipped upside down. So we end up with this instead. And now what we have is we have something where we have I0 divided by I0. So these two I0s cancel, and we're left with 10 log IB on IA. But we have expressions for these. We calculated them earlier and we found them to be given by this. So if we just take these two and we plug them into here, what we find for the difference in these sound levels is this. That's going to be 10 log. So plugging this in, we're going to have power divided by all this garbage, 4 pi. Yes, 4 pi, so 2d squared. And that's all got to be divided by power divided by 4 pi d squared. And once again, we have a fraction divided by another fraction. So this then we can write like this. It's just going to be the fraction in the numerator multiplied by the fraction in the denominator turned upside down. And here we see a couple of things that it can cancel. We have a 4 pi divided by a 4 pi, and we have a power divided by a power. So this is going to be 10 log d squared. Now if we just expand out these brackets, what this is going to be is 2 squared multiplied by d squared. And so suddenly we have something else that can cancel. We can get rid of these d squareds as well. And so finally we're just left with 10 log 1 on 4, since 2 squared is just equal to 4. And if I plug that into the calculator, we get that that's 10 times log of a quarter, which is minus 6.02. And that's going to be in decibels. So what this is saying is that when the man walks from a point A, doubles his distance from the source, the sound level that he hears is going to drop by 6 decibels.